Hello and welcome back to a new video in my real-time rendering series here on the Lötwig Fusel channel. Now in today's video we're going to talk about the rendering pipeline. Now the rendering pipeline is the workflow that the GPU is doing for us in terms of rendering. So everything that the GPU renders, for example here that image from Watch Dogs, went through the rendering pipeline. And that's what we want to explore today, because we have in the last video written the generators to upload geometry on the GPU, and now we want to render the geometry. And rendering the geometry is only possible if we are using the rendering pipeline. And in fact, that's everything that we need. Geometry on the GPU and the rendering pipeline and a bit of infrastructure stuff, and we are ready to render our first image. That's where we want to go to. We want to render our first image, our first triangles. So let's get started and talk about the rendering pipeline. Now a quick disclaimer before we begin. I highly recommend watching my DirectX 12 tutorial series, because in this video, again, we're going to talk about the DirectX 12 rendering pipeline. I'm not going to only talk about the rendering pipeline, but that's something that we're getting to in a second. However, everything that's explained is kind of like in the concept of DirectX 12. We have DirectX 12 examples. We are talking about HLSL, so the DirectX language for writing something called shaders. And everything is kind of like DirectX 12 focused. Other rendering APIs like Vulkan, OpenGL, DirectX 11, Metal, whatever you want to use, they have a similar architecture, especially like Vulkan and Metal, because Vulkan and Metal are also modern rendering APIs. So if you're kind of like comparing DirectX 12 to Vulkan, you're gonna see a few differences, but the general concept shall be the same. However, still we're gonna use DirectX 12 for the video series, so it's recommended that you have watched my DirectX 12 tutorials, or at least that you are aware that I have DirectX 12 tutorials. So if you want to know something a bit more in detail, you can watch these videos there. Alright, so let's talk about what we want to learn in this video. Well, we're going to take a look at what we already have done on GPU and what the next steps are and what steps are required, and I'm also going to tell you why these steps are required. Now, the next thing that we're going to talk about is the rendering pipeline itself. So what is the general concept of the rendering pipeline? How would a generic rendering pipeline look like? And after that, we're going to talk about the DirectX 12 rendering pipeline, and especially then even after that over the other DirectX 12 pipelines as well. Because DirectX 12 is currently providing us 3 different pipelines that we can use. We're gonna stick to the classical graphics pipeline, the classical rendering pipeline, for quite a while. The other ones, we might explore them as soon as it fits. Alright, so let's get started with the next step that we need to do. So what we have already done in the last video is we have loaded geometry from an FBX or OBJ file. We have converted it into a format that the GPU understands. So we have defined that our vertex should look like that, X, Y, Z, and W. And what we have done is we have loaded with ASM the FBX file, and then we converted the FBX file into vertices with like X, Y, Z, W values, and in indices, so that we know which vertices make up a triangle, because that's how the GPU understands geometry. Next thing that we have done, we haven't quite done that yet, we have uploaded the GPU, the geometry to the GPU's memory. There's like probably 2 lines of code missing, maybe 4 lines of code. It's not going to be very complicated, the addition that we need to do. I'm going to do this addition as soon as I have my DirectX 12 stuff implemented. But we just assume for now that we have already uploaded that. We have written the generator, even though it's missing the part of uploading. I'm going to assume for today's video that this upload has been already done. Now, what are the next things that we need to do? Well, there are actually 4 high-level steps that we need to do. So the first step is that we need to position the geometry on the screen. Now, you might ask, why do we need to position the geometry on the screen? Well, let me show you a quick example. So if you are creating some geometry like the Suzanne monkey that we have already done last video in Blender, it is by default always positioned at a static position. In this case, Suzanne is at the center of the screen. This does not need to be the case. It could also be that Suzanne is a bit lifted to the top, but it's always one thing that's in common. If you import the model, it is always at a fixed position. So Suzanne is always going to be just elevated here in the Y direction. In case this is Y, I don't think it's Y in Blender. In Blender is Z, but the general idea is if you are modifying your geometry in Blender and move it up in Blender, it's always going to be at that position. So if you're exporting the geometry and you're uploading this to your GPU, it kind of like always has the static position, which is positioned in this case a bit above the origin of the coordinate system. So the problem that we have is that all geometry is always going to be at the same point. And that is why we need to transform the geometry to the correct point of the screen. Actually, there are 3 steps involved in doing that. So that single step here inside of the presentation that position the geometry on screen is actually done in multiple steps, actually in 3 steps. The first step that needs to be executed is that the geometry needs to be scaled and positioned. So the general idea is if you want to make Suzanne bigger, it needs to be scaled up. If you want to rotate Suzanne, it needs to be rotated. And to position it in a 3-dimensional world, you need to translate it to some other position inside your game world. So the general idea is what you need to do is, first of all, take that static position from within Blender and transform it to a position that's meaningful to your scene that you want to render. Now, after you have done that, you need to take into account the camera, because the camera can move around the scene and you are always kind of like looking down at a different part of the scene. You need to transform the geometry into the space of the camera. So after you have transformed it to a position in the world, you kind of like need to apply a transformation so that the geometry is now positioned on the camera space. This can have multiple results. For example, if the camera is not looking at the object at all, it's positioned behind the camera and thus will not be rendered. If the camera is directly looking at it, it might be transformed a few centimeters to the left, to the right, whatever, and then basically it is positioned in the space on the camera. Now, after you have positioned this on the space of the camera, you need to transform it in the space of the screen. Your screen in general is not aware of depth and it's not aware of 3-dimensional concepts. So what you need to do is you need to do something called projection. And projection means that you kind of like fake the effect of a 3-dimensional world on a 2-dimensional space. In this case, the 2-dimensional space is the screen. What's also happening is a remapping of the distance to the camera. The distance to the camera is remapped by cropping away objects that are too near, or not objects, but in this case vertices, that are too near to the camera, and also cropping away triangles that are far away from the camera, and also remapping the distance to the camera so you have it in a proper format that we can later on use for something called depth buffering. But we're going to go into all of the details in the future again when it's fitting in the tutorial. Now, after you have positioned the geometry on screen, now you kind of like have triangles in the correct location on the screen. You need to transform these geometry to pixels. So after the triangle is ready and placed on the screen, we need to do the step of rasterization and actually determine which pixels are covered by the triangle. Now, after we have determined all these pixels, we need to compute the color value for each pixel, because just having pixels there wouldn't really change anything. If all pixels are black, this doesn't really matter that we transformed and everything is still going to be black on our screen. But in this case here, we want to compute the actual color value for each pixel. So we take each pixel that we have computed from the triangle, and then we kind of like compute a value for that, and that value is then the final value that this pixel of the certain triangle shall have. And this is what then the last step is involved. The last step is involved in actually sending the pixel to the screen. There are also some more rules that need to be applied there. For example, if we have transparent geometry, so geometry that shall be translucent, so you can see something that's behind, this needs to be correctly blended with the geometry that's actually completely opaque and behind the transparent object. It needs to have a correct blending step. Then what also needs to be done is it also needs to be checked if the actual pixel shall even be displayed. For example, if the pixel is kind of like related to a triangle that's behind a different triangle, the pixels behind only the front pixels shall be visible, so all pixels that are behind other pixels shall not be displayed, and that's all something that needs to be taken account into that step here as well. So these 4 things are the things that we need to do, and we do this by using the rendering pipeline. Now, what I have done here is I've made some general terms here. This is kind of like a generalized rendering pipeline. So we always start with the raw data, the raw geometry data. The raw geometry data is then modified and transformed. So we are modifying and transforming this geometry. After we have modified and transformed this geometry, we want to convert the geometry to pixels called rasterization. And after we are done with that, we need to process each of these pixels, and the output are going to be the raw pixels for the screen. So this is like the general workflow of a rendering pipeline. Now, what we want to take a look at this is, of course, the rendering pipeline of DirectX 12, so what we are actually working with and how it's actually implemented in the GPU. We're first going to take a look at the classical rendering pipeline. There's also a bit more modern version of the rendering pipeline called the mesh shading rendering pipeline. However, this is not like very widely adapted. It is having definitely its purposes, but we want to, for now, first stick to the classical render pipeline, which has grown over years. So the general idea is, when the first GPU came out, the rendering pipeline was basically just like one step or maybe two steps. One step like converting triangles to pixels, one step maybe coloring these pixels, and one step sending the pixels to the screen, and everything else just needs to be handled by the application. So so the first basic rendering pipeline was very simple. However, the rendering pipeline has evolved over years and is now at the point where it's quite complicated, and so that you're just seeing this is the current state of the rendering pipeline in DirectX 12. Now, this is a very big image that looks very intimidating. And what we want to do is we want to break this down step by step and take a look on what's really relevant for us and how this all comes together and how this is all getting relevant with a few examples on how it's actually been used. Before we start with that, I want to quickly break this down into a few parts. The actual rendering pipeline, kind of like the function that the GPU is doing, is actually everything that is inside of this black box. This box here is also kind of like related to that. Later on, we're kind of like going to limit the rendering pipeline to the right part of the image, and then we are taking a look at this. Everything that's on the left part here has something to do with the data for the rendering pipeline. So the rendering pipeline has multiple stages that flow from top to bottom. That's the actual pipeline. And the actual pipeline, of course, needs some data it operates on. And the data is coming from the left. So everything that's on the left here is kind of like the data for the rendering pipeline on the right. Now you can see that the actual parts of the rendering pipeline have different colors. We have the pink color. This color here means that it is a fixed function unit. A fixed function unit means that it is a feature that we cannot really influence. We can configure it and we can somehow kind of like tell it how to do its job, but we cannot really change it in its fundamental, or we can't say, all right, just do that one part. This is kind of like a fixed function thing that is maybe even implemented as dedicated hardware in the GPU. So dedicated circuits that are doing that specific purpose. And we can only kind of like tell it how to work. For example, the input assembler has multiple modes on how we can run it and multiple input slots that we might be able to use. And that's it. We can't configure really more on it. Now, the other colors that we have in here, these like dark blue or this light blue and this dark blue or a bit darker blue, it's not really dark blue, it's more like blue and light blue. These are so-called shaders. Now, shaders are programs that run on the GPU. A shader in general, it is an application that the GPU is executing in there. We talked about this, I think, last video, 2 videos ago, the CUDA cores. On NVIDIA, it's a CUDA core. This is like the unit that is doing the math. And actually, these shaders are executed on these CUDA cores on the streaming multiprocessors, staying at the NVIDIA terminology. This is kind of like the actual application that's then running on the GPU. Now, you can see that we have multiple of them, like vertex shader, hull shader, domain shader, geometry shader, pixel shader. So actually, if we have a very complicated rendering path that we are doing, so a very complicated stuff that we want to render, that's called rendering path. A rendering path is kind of like one rendering step through the pipeline with a specific configuration. We can have up to these 5 shaders that are actually invoked step by step with different input data and different output data. Now you can see that one of these shaders is kind of like the normal blue, while the other ones are only light blue. The light blue ones are all optional. So if you want to build a very, very basic rendering steps or very rendering paths, you just actually need the vertex shader. You only need the vertex shader, nothing else is required. We're probably also going to start with that so that you can see how easy it is. And then we're going to try to add more step by step and actually talk about how all of these come together, and then we're going to go to on how the actual usage of that is and how we can abuse the pipeline to actually do what we want to have it doing. Now, Let's actually go into the pipeline and take a look at all of the parts step by step. We're going to start with the input assembler, and the input assembler is exactly doing what the name is suggesting. It is assembling the input. In general, what it does, it assembles primitives out of the vertex and index buffer. We talked about that we are converting all of our triangles to vertices and indices, and all of the vertices stored in the vertex buffer. The general idea of the vertex buffer, vertex 0, 1, 2 until vertex n-1. And the index buffer, on the other hand, is just always like a pair of three 32-bit integers that are actually telling the GPU which vertices are kind of like covered out of the triangles. And the job of the input assembler is actually taking the index buffer and the vertex buffer and producing triangles out of these two. So it's kind of like taking a look at the index buffer, reads three indices, reads these two vertices, passes it down through the pipeline. That's kind of like the basic idea. Now, of course, it's a bit more complicated because we can have also points, we can have lines, and we can have triangles. So, of course, the input assembler can also work with points, lines, and triangles. And in general, what we use is point list, line list, and triangle list. The input assembler can do this with and without an index buffer. If you're using it without an index buffer, it basically takes two vertices for a line, three triangles, or three vertices for a triangle, and always then goes on for the next three. If you always have an index buffer attached, then it's of course concerning the index buffer and loading it properly to the index buffer. There's a different type that the input assembler can do. This is something called a triangle strip, or triangle strips if we have plural. The idea of a triangle strip is that you don't need an index buffer. However, also do not duplicate triangles. So a triangle strip is in general triangles that are connected together. So for example, if you would have a quad, you could describe the quad out of four vertices and two triangles. And the idea of a triangle strip would be that you are kind of like defining the vertices 1, 2, 3. And what the GPU will then do, or the input assembler will then do, it will discard the first triangle that you have specified and take the next one from the list, or from the vertex buffer, and then the resulting three vertices are made up out of a triangle. So every following triangle is always sharing two vertices with the previous triangle. And this is then kind of like used in a pattern of a triangle strip, so that they are kind of like connected. Now in DirectX 12, it's defined by these structs. I don't think that we're going to take a look at them now. If you are interested in how they work in DirectX 12, take a look at them. This is how they are configured. Now, after the input assembler has assembled the input, so actually has assembled triangles that are composed out of vertices, the vertices are passed to the so-called vertex shader. The vertex shader, as the name stands, shades vertices. And shading in this case, I told you that it's an application that's running on a GPU. So it is actually some code that is executed on a per vertex base. So every vertex that the input assembler assembles is passed to the vertex shader. Now, the vertex shader is written in a language called HLSL, which stands for High Level Shading Language, which is the DirectX 12 code for shaders. In general, it is very similar to C or C++, probably more C++, because I think it is somehow object-oriented. You cannot really use classes, you can use structs, however, you can also use templates. So yeah, it's kind of like a mixture of C, C++ there. Now, the general idea of the vertex shader is that everything that needs to be done on a per frame base, so for example, positioning the objects on the screen, because the position of the camera changes every frame, the position of the objects might change every frame, every time we're rendering an image, these positions might change, and if these are changing, or can change every frame, then we want to actually have the code for that in the shader and not on the CPU side. So the general idea is that we are running a small bit of code that is doing a bit of work on the GPU, then doing a lot of work on the CPU and always uploading the data again. Now, in this case, I already told you that it's, for example, used to transform triangles. We're probably going to stick to transforming triangles for quite a while. This is basically... yeah, mainly you're probably going to always have the vertex shader as a very simple code that is just transforming triangles, at least if you have normal geometry. If you have a bit more complicated geometry, the vertex shader might do more. But the general idea of a vertex shader, it's always just transforming triangles. In this case, as I already told you, we are starting like at the model space, how we got it in Blender. We are converting it to the space, how it is like positioned in our screen. We converted it to the space how it's in our scene. So it's then in so-called world space, and after that we are converting it to the view space, so to the actual space where the camera is located, and then we are converting it to screen space, and this operation is called MVP. So model, view, and projection. Model, view, and projection. Model stands for kind of like how the model is positioned in the screen. View stands how it is like viewed from the camera, and projection stands for how it is projected onto the screen. Now I have a very simple vertex shader here on the right as an example. This vertex shader is not doing fancy MVP stuff. This is just doing a bit of scaling. This is actually now one-to-one coming from my DirectX 12 video series, and we're going to take a look at the DirectX 12 code in any second so that you can see what it is really doing. Now, the general idea what's happening here is that we have a main function, and the main function is always a function that the code executes. In this case, main here, curly brackets, it is the shader function that's actually running. Everything above here is kind of like infrastructure for that. For example, we have two includes, which are including some other stuff that we are not aware of yet. Then we are defining like a struct, triangle parameters, and then we are kind of like instancing these triangle parameters as a constant buffer, which is then called parameters and is located at a register B1, which has something to do with mapping to a root signature, but we are getting to that when we are done with the pipeline. Now, the general idea here that's happening is that the main function is called on a per vertex space. You can see that the input parameter is a VS vertex data. VS vertex data stands for the structure that defines the vertex data. It's actually defined in demo.hlsli. This is kind of like an include file, like an H file in C++, while HLSL is kind of like a CPP file. Now, we really don't care what's inside of this vertex data. In general, it is just the container that the input assembler has assembled. So you have configured the input assembler and your vertex buffer in a certain way, how your vertex is laid out, or your vertices are laid out, and the input assembler is then correctly assembling that and passing this here as a parameter into the vertex shader. Now, as you can see, I also have an output format, the PS vertex data. This is now actually the pixel shader vertex data, because actually the concept of pixels is not available on the GPU. Pixels are also kind of like treated like vertices. And pixels are actually also originating out of vertices. So you have like the three vertices of a triangle, and they are getting interpolated in the correct values for each pixel. And this is why this is called PS vertex data, because it's the vertex data on a per pixel base, which is the data that we now actually want to transform. In this case, you can see that we are creating an instance of that, and then we are assigning the position to that. The position is actually a custom layout that I have defined here in this case, because again, vertices are just containers. You can put in everything that you like. Now, as you can see, position is a float 4. This is why this is assigned to a float 4 value, and this float 4 value is composed out of that term and the term on the right, or the two terms on the right. The two terms on the right are just static values. You can see like X and Y value are computed by that. Z value is static at 0, and W value is at 1. So very simple. Now the operation here on the left, it is a mathematical operation. So you can see that we're actually taking the input vertex's position and we are multiplying this by the parameter scaling. You can see this was coming from here. The scaling is the float 2 that's here. And it was kind of like registered as a constant buffer at register B0 with the name parameters. This is how we can access that here. Now the next step that we are doing is we are assigning UV coordinates. You can see that they are just plainly copied over. And after that, down here, we are returning the vertex as a output vertex. And that's it, a very simple vertex shader. Now, can we actually see what's going on here? Yes, we can actually take a look at this in my old DirectX 12 code. All right, so this is the code for my DirectX 12 series. This is actually where the shader is attached to. And what's going on here is that the constant buffer here that was used for the scaling is actually accessed here in that block called logic. So you can see constant buffer 0, scale, which is kind of like the parameter that we had, to floating point values 0 and 1 is kind of like assigned here. You can see if I press the VK left, which is the virtual key code for the left key on the keyboard, you can see that I'm actually adding a 0.2 float to the scale. If I'm pressing the right button, I'm subtracting 0.2f from the scale. If I'm pressing the up button, I'm going to go to the y value, and I'm also adding 0.2f to the y value. And if I'm pressing the down button, I'm subtracting 0.2f from the down button. So basically, if I press the left button, I'm scaling the x value up. If I'm pressing the right button, I'm scaling the x value down. If I'm pressing the up button, I'm scaling the y value up, and if I'm pressing the down button, I'm scaling the y value down. Now the initial value should be somewhere down above here. So the default value you can see is at 0.5f. So we are kind of like starting with a half scale operation, which is by default like halving all the coordinates. Now, if I start this application, we can actually take a look on how this is, how it's looking. And what you can see here is that we have one triangle. Actually, you can see that the triangle is textured, so there's a texture applied to it. This is kind of like done by the pixel shader, but we're going to get to that. And you can see that it's kind of like covering the half of the width of the screen and the half of the height of the screen. So you can see that kind of like the scaling operation works. Now, if I'm now pressing the up button, you can see that the triangle actually grows. Can actually grow this over a scaling value of 1, but somewhere it escaped. I think I capped it at 2 or 1.5, I'm not quite sure. We should have taken a look at it in the code. And also the down button left and right is also working. So you can kind of like see that we are changing the triangle if we are pressing buttons. Of course, if I'm pressing multiple, it doesn't work. Now, just to explain this again, when we are comparing this to the actual implementation in here, it's very simple. We are taking this vertex position and multiplying it by the scaling. Since the position is normally at 1, which would mean like a fully screen covering triangle, we are dividing this or multiplying this by 0.5. We are kind of like dividing it by half, and the position is only going to be the half of the vertex. So that's actually what's going on here. And this code is executed on the GPU on a per vertex base. Now, as soon as the vertex shader has processed all vertices, we are getting to the tessellation stage. The tessellation stage is an advanced stage, and I don't want to go into too much details on how tessellation works. However, it is important to know. The general idea of tessellation is that we are taking a triangle and converting it into more triangles. Now, you can see here on the right, we are having an example. You can see that we have one big triangle. This is converted into many, many more triangles, and this is then outputted as many, many more triangles. Now, the tessellation stage has actually 3 steps: a hull shader, a tessellator, and the domain shader. So all of these 3 parts in the pipeline are used for tessellation. So the general idea is we are having a shader, that's some custom programmable code. Then we are feeding the data in a tessellator, in a fixed function unit. And then the tessellator is invoking the domain shader, which is again a programmable unit. Now the job of the tessellator is very simple. The tessellator just takes a triangle and makes more triangles out of them. It's doing this with something called the tessellator factor, the tessellation factor, and the actual tessellation factor tells the tessellator how many times it shall like subdivide the triangle. You can see that it is following a pattern here, so the pattern is always the same. So it's really simple to have this as a fixed function unit. We just need to tell it how many times we want to have it subdivided, even through most of the time on a per edge. So most of the time you can actually provide 3 tessellation factors for each edge of the triangle. And what it's then doing, it is kind of like taking this into account and generating a certain triangle pattern inside of that existing triangle. Now, the general idea is that the hull shader is executed before the tessellation, and the job of the hull shader is to prepare the data for the tessellator. So in general, what it does, it prepares something called control points. Control points are points placed onto the triangle. So you can see, for example, that one it's a control point, and the control point is kind of like passed through the tessellator and comes out as a simple control point as it is after the tessellation. The interesting part is the actual tessellation factor. So the tessellation factors kind of like define how many triangles we got. And if we are creating new triangles, we are of course creating new vertices, right? We have the 3 existing vertices, but we are creating many, many vertices in between. And that is actually the whole purpose of tessellation. We want to have more vertices that we can actually modify. Okay, and after the tessellator has produced the new vertices, they need to be transformed in the domain shader. shader. So the domain shader is called per generated vertex, and it can also consume the control points. And the general idea is that the domain shader takes the newly generated vertex and modifies this according to the data stored in the control points. So idea, it's very simple. The hull shader is generating ourselves control points. Most of the time, I think, even on a per triangular base. So you kind of like get the 3 input vertices of the triangle, and then you are kind of like generating the control points. In the hull shader, you're generating the tessellation factor, and then every vertex that is produced by the tessellator itself is then shaded by processed by the domain shader, which has access to the actual now generated vertex and the control point that has been maybe transformed by the tessellator, but in general it's more like a one-to-one copy from the input. So it consumes these control points to know how to modify the vertices, and at some point it's finished, and what then happens is that it outputs the vertex data. So the vertices that have been generated are now transformed by the domain shader, and the domain shader outputs them so that they can continue flowing through the pipeline. Now, the next step in the pipeline would be the geometry shader. However, I want to quickly go and take a look at the stream output, because we have an optional stage called the stream output after the domain shader. Now, the stream output, the concept of stream output is very simple. The concept is that we can output the geometry that has been generated by the tessellator. So the input assembler had some very basic triangles assembled. They have been transformed by the vertex shader, and now the tessellator had its job in tessellating the geometry. And now we are having the option to actually output this back to VRAM, so that we don't need to run tessellation multiple times. Or for example, this is the example that I have used here, we could use the GPU to tessellate a terrain according to some transformation data of the player. If the player is moving through snow, it is maybe modifying that snow. This is something that could be done in according with the simulation on the GPU. And what we are then doing is kind of like storing the tessellated geometry into VRAM, and we can then load the tessellated geometry back on the CPU by copying it from VRAM to the system RAM, and then we can do this to update a collision mesh, so that kind of like the engine is aware that the terrain has been deformed. So we can then use and abuse the tessellated geometry on the CPU. Now, after the tessellation stages, we have the geometry shader. Now, the geometry shader is way older than the tessellator itself. So one thing that you could actually do in the geometry shader is doing software tessellation. Software tessellation is not very efficient, and that's the main reason why we even got the tessellator unit, because the geometry shader is not really good for tessellating. However, it has different purposes of usage. For example, the transformation of primitives into other primitives, or the multiplication of primitives. Now, multiplication of primitives, it's quite simple. We already done this at the tessellator. The tessellator can take one triangle and make multiple out of them. So that's not really something that you would use in the geometry shader. You wouldn't use it if you really want to doing tessellation. However, what you can do is you can, for example, transform points into triangles or points into quads. Points into quads is a common thing that I have also done with actually an example code here on the right. And the general idea here is that the geometry shader gets an input vertex, and it transforms, or it compute output vertices out of that. So kind of like the vertex has first been shaded with the vertex shader, it has processed them, and then it's kind of like passed to the geometry shader. Now, what you do is you have kind of like an input primitive, which could be, for example, a point, a line, or a triangle, and what you do is you produce one or multiple output primitives. Example here, again, as I already told you, we can take a two-dimensional point and convert it into a quad. A quad is transformed out of two triangles, and in general, what we then need to do in the geometry shader is we need to produce 4 vertices. Now, the geometry shader is also working on the concept of triangle strips. This is why I also went a bit into detail on to explaining how these triangle strips work. So if you would want to take a point and convert this into 4 quads, not 4 quads, into 4 vertices, aka two triangles, you would need to do it like that. For example, in this case, I have defined 4 vertices, vertex 0, 1, 2, and 3. Then I populated the vertices with some data. And finally, what I've done is I've called an output stream and told the output stream to append the vertex. Now the output stream is an input-output component of our shader. The input-output component is of type triangle stream. So it is a stream of triangles. You also, of course, need to define it a format. And the general idea is you can append data to it. You can see, for example, here's a semantic on top of the shader that says maximum vertex count 4 or max vertex count. The max vertex count means how many vertices are maximum stored in this triangle stream. It's kind of like how many data or bytes need to be allocated for that stream in the worst case. This case is really simple. I'm always appending 4, so I define 4 here. And generally what you're doing is you're telling it here's a vertex, here's a vertex, here's a vertex, and it's of course required to be in the same order. So the first 3 vertices are joined to a triangle, and in this case the last 3 vertices are joined to a triangle. So 1, 2, 3. This one is discarded. That one is the new one that gets joined onto there. So this is kind of like the same concept that we had on the triangle strips, and this is in general how the geometry shader works. Because in general the idea is we do not have the concept of indexing at this stage in the geometry or in the rendering pipeline. The concept of index and vertex buffers is a concept that's purely consumed by the input assembler, and after that the concept is no longer there. So we kind of like need to provide information on triangles. In this case it's the triangle stream. The triangle stream is kind of like a data stream that can later on be decoded by some fixed function hardware that are kind of like coming with the geometry shader to then output it to normal triangles again. Now, I don't want to go into too much details here. One maybe information is that you always need to call restart strip as soon as you are done, because restart strip is kind of like saying, all right, the data is ready. I want to make it reusable. But that's really just in the implementation detail that we are going to get to it. Now, what the geometry shader does is nothing more than what happened previously. It outputs vertices, newly generated vertices, converted to triangles, kind of like in a triangle context. And these vertices are then passed onto the rasterizer. Now, the rasterizer is a very important step on our pipeline. The rasterizer is a fixed function stage that converts geometry into pixels. Now, the general idea of the rasterizer is that it's a fixed function, but it can also, of course, be configurable. And the idea is, give me a triangle, a point, or a line, whatever, and convert it into the pixels that it is actually covering. Now, in general, what the rasterizer is also doing is it's discarding stuff. If something is not in the range of the screen, it's discarded. Not computed anymore. The pipeline discards it. It's not no longer in there, functional, usable. It's just away. It can also be concerned to actually discarding triangles that are on screen but have wrong properties, the binding order. So how the triangles is defined as 1 to 3 or 3 to 1. Depending on that, you can discard triangles because you kind of like see them as not facing in the right direction. But this is also something we're going to get to all of these details when we have the problem that this is then actually solving. Now you can see a bit of an example here. You can just see a few triangles here, and you can see the colored pixels that are kind of like affected. You can see this kind of like doing this on a per coverage base, so it's kind of like always checking if one pixel, how much one pixel is covered by a certain triangle, and if the coverage is high enough, it is automatically passing this on to the next stage, which is the pixel shader. Now, of course, the rasterizer is configurable. There is something called conservative rasterizing. Conservative rasterizing means if the triangle is touching the pixel, always output it. Now, the general idea is, even through this slide or this Microsoft image here might assume that you actually have some coverage information available, like these like dark and light colored pixels. No, you don't. It is a binary operation. The rasterizer in general makes a binary decision if a pixel is rasterized or not, and this is why we actually need anti-aliasing later on in our engine. And anti-aliasing is the process of actually detecting these sharp edges and blurring them with the other data. So for example, if you're having two triangles that are kind of like next to each other and have a hard change of color, but it's kind of like a soft edge, then you of course want to blur them together so that they are kind of like looking soft. There are many ways of doing anti-aliasing, but we're going to get to all of these in the future. Now I have another example for you here and how the rasterizer can also operate. This is the rasterizer with multi-sample anti-aliasing available. Multi-sample anti-aliasing basically means render at a higher resolution and then convert it down. That's not really the concept. This is actually like SSAA, super sampling anti-aliasing. Super sampling means just render at the double of the size of the screen and then do a custom filter over everything so that this is combined. Multi-sample anti-aliasing works a bit different. It works with a sampling pattern, with a proper coverage analysis, and actually having the same resolution but having more samples on a per pixel base. You can see all these points are kind of like sample locations, and here a sample hit it, here 2 samples hit it, here 3 samples hit it, here 2, and there also 2 samples hit it. Do we have a triangle which has all 4 samples? Yeah, this triangle covers all 4 samples of the pixel, and the general idea is that we are doing way more advanced sampling with a certain sample pattern, and later on we have a resolve step where we actually are taking these sample locations and then merging them into a proper texture that can be displayed. Multi-sample anti-aliasing is a whole different topic on its own, where we're going to at some point have a sub-series or a kind of like sub-chapter of the tutorial, which is called anti-aliasing, and then we're going to discover all of the anti-aliasing methods that we have, including SSAA, MSAA, probably also SMAA, and all the different anti-aliasing techniques that we have. Maybe also like the NVIDIA and AMD proprietary stuff like FXRR, TXAA. There are so many ways of doing that. DLSS. DLSS is a bit different, but there's also a DLAA, deep learning anti-aliasing. DLSS is also kind of like doing some anti-aliasing, but that's also something that we want to talk about in separate videos. General idea, rasterizer takes triangles, converts it into pixels, however it is doing that. Alright, so now we want to talk about the pixel shader, the last programmable unit in our pipeline. Now the idea of the pixel shader is that it becomes as an import vertices. Now you might be a bit confused and say, why do we get vertices as an input to the pixel shader? Now the problem is that pixels are not really a concept on a GPU. We until now just had vertices. Triangles were composed out of vertices. However, now we kind of like detected pixels that are inside of a triangle. Now, how do we transform the data that was coming from the vertices to the triangles? Now, in general, we could just pass always the nearest vertex to it. However, that's not a good idea. We have 3 vertices that are kind of like of the same format. And each pixel is differently influenced by each vertex. And the idea is that the GPU is doing interpolation. In this case, I think it's called bicentric system of order 3, which means basically 3 vertices that needs to be kind of like transformed or interpolated. It's kind of like an interpolation with 3 input variables. Interpolation based on 3 vertices and kind of like 3 distance to the 3 vertices, and then it's doing its job. And the idea is that you take these 3 vertices, all of them have the same data layout, all of them have values on a per layout component, and you are doing this barycentric interpolation between these 3 values to find one value that is influenced by the 3 values of the 3 vertices. Now the format is still going to be a vertex, right? Because the output of the vertex shader, the domain shader, geometry shader, depending on what you have enabled or used, it's always going to be a vertex. And the data format is a vertex, so the vertex is also fed into the pixel shader. Now the vertex is no longer the original value. Now the vertex is actually the interpolated value for that pixel, but it's still like a vertex. The final output of a pixel is only outputted after the pixel shader. Of course, you can completely bypass the pixel shader. If you're bypassing the pixel shader, the geometry shader also already needs to, or the vertex shader, the domain shader, or the geometry shader already needs to specify the values that the actual output merger needs on a per pixel base. But a general idea is that the pixel shader is kind of like the unit that converts your idea of a vertex, of a transformed vertex, into the concept of a pixel. Previously to that, most of the time, if you're doing rendering with like good geometry, with like textures and high fidelity geometry, the concept of a pixel, the actual color of a pixel, the concept is only available after the pixel shader. In this case, you can see this here myself as well. The input data was UV positions the input data were in normal positions, and now the only concept of a real color that's outputted is in the pixel shader, the output of the pixel shader. Now, here the example of the pixel shader is also quite simple. We have, again, a few includes, the same ones that we had previously. Now we have a bit of noise at the setup that's going on. You can see that we are loading something called a sampler, called text sampler, from register S0. We are loading something called texture2D with float 4 components, or 4 floating point values as a component, in something called texture from a register T0. We are loading a 4 component floating point value called myCfloat from a register B0, and then we are taking this data into computations down there. Now, what's going on here is very simple, right? The input is this vertex data, pixel shader vertex data, it's called in this case, and the output data is a OM pixel data, and OM pixel data, PS out, is then populated here. It has just a color value in this case, which is a 4 component color, because RGBA, that's kind of like the format you always have, even through your screen is not always gonna be, it's not gonna be transparent, right? But still, the output format most of the time is RGBA, and then the GPU is mangling this into a proper format on how to transform it to the screen, but that's a different story. Now, the idea here in this case is, again, we are having this color value, still a float 4. It is converted out of that component and that component on the right. The right component is a 1.0 value, which basically means that it's completely opaque. It is not transparent. Transparency is required at some point in our engine, even though our screen does not support it. Now you can see that we are now doing some mass operation on 3 component floats. So you can actually see that we are accessing this myCfloat, which is a 4 component float. However, we are just taking the RGB data, so the X, Y, Z, the first 3 component. And as you can see, kind of like the scheme on the GPU, a float 4 can be accessed by X, Y, Z, W, and also RGBA, and also UVWX, I think. Not quite sure. UVW is, I think, the coordinates. I'm not quite sure how the 4th component is called there. Yeah, so the general idea is we are taking that RGB color values from the constant value that we have, and we are multiplying this with the RGB value that is coming from the texture. And the texture has a method called sample, and the sample method here required 2 parameters. It's required the actual sampler. The sampler is kind of like the configuration, how to sample a texture. On the GPU, it looks a bit different. On the GPU, the sampler is a hardware unit that kind of like gets more like the texture as a parameter, but in HLSL, it's more like, hey, this is my texture, I want to sample from it using that sampler. Even through the hardware might implement it differently, at least from the NVIDIA diagrams, it looks like it. The second parameter are the actual coordinates of from where do I want to sample at the texture. And, well, how does the result look like? Well, the result looks like that. Right, we have a triangle that has been sampled from texture. Now, you can see that the multiplication is currently not doing anything because it is the color as it should be. However, what we can do is we can actually influence the implementation here, this multiplication, this myCfloat. This myCfloat in a DirectX 12 example code that I have done, it is defined, where is it? It should be defined somewhere. This is the constant buffer with the scaling. Where is my 4 component float? Need to find it. Ah, there it is. Here, float, it's called FLT. Yeah, not really named properly, but this is kind of like these 4 floating point values that I'm assigning here. You can actually see they go in there, which is kind of like defining how they are used. Well, but the general idea is we can take that floating value and actually change it, right? For example, what I can do is I could just show the red component. So I could add the multiplication for blue and green to 0 and just leave the multiplication of red at 1. And this should give us a completely red triangle, because we should just have the red component in here. And surely enough, I can only see the red component. I still see the eye because it's still used from the texture, right? It's not completely red because still the red information from the texture is accounted. However, the other color informations from the textures are not accounted here. Now I can do this also differently. I could also, for example, mix these colors. I could write a function that works over time. Or I could just make the whole triangle, a few of the colors a bit dimmer. If I would do this, for example, something like that, it should, yeah, it's looking a bit more greeny because I have reduced the red and blue components, so it's way more green. But that's not really something interesting. You want to see something interesting and play a bit around here with my DirectX 12 code. Of course you want that. And we want to do this by abusing a bit of more of my get async key state, in this case vk space. Spacebar is always something amazing to tinker around with. And what I want to do is I want to have a police siren. So a police siren that is blue and green. No, blue and red is it, I think, in the US. In Germany, it's just blue and off, or blue and white. But I want to have like this police scene from the US. So the general idea is one RGB. That's kind of like the RGB concept here. And what I want to do is, first of all, I want to have it blue, and then I want to have it red. So we're going to start with a blue one, and if we're pressing space, it should be red. Now, if I do it like that, of course it should work. It's completely red. Why is it so dim? That's not really what I thought I will get. Oh, of course. Yeah, because it needs to be that one. It's not 0.1, it needs to be 1.0. Yeah, it would be maybe a bit, I think, a bit more better if I would then write that like that. That looks a bit better and not that confusing. So now I should have a red triangle, and if I press the spacebar, it should be blue. And now if I spam my spacebar, I have a police sirening triangle with some texture on it, with the all-seeing eye, Illuminati eye. Yeah. So that's amazing, right? I'm still thinking that I was really funny of taking exactly that texture. Required me to actually order a dollar bill from eBay, doing high quality photography on that, transforming this in Photoshop, applying some color correction, making sure that's correctly transformed. That was quite some work and some money associated with actually getting this dollar bill ready for the tutorial series back then in DirectX 12 times. So yeah. Now, as I told you here, that's a really simple way of applying color to your images. Of course, the concepts are way more intense and way more complicated in reality. But we are not going to overdo this in this tutorial series. We're not getting into the point of actually doing memory management, swapping out textures that we don't need, swapping out geometry that we don't need. That's not going to be the concept, at least not for the beginning. For the beginning, we're going to do a very plain tutorial there. Now I have another example for you here. I don't want to go into that one actually. I think we're going to just skip it because it would be too complicated. We're going to talk about that when we are getting to the third rendering. Now, after the pixel shader has outputted pixels, we need to do something with these pixels, because just pixels with some color information attached, they are not useful. They are actually going into something called the output merger. The output merger job is to write the color values to the so-called render target. The render target can be really anything. Most of the time, at least for now when we get started, the render target is going to be our back buffer, and the back buffer that we are using is going to be the screen. However, you could also use the output merger to render to a texture. You do not need to render to the screen. You do not need to display anything. You can use DirectX 12 to do some work in the console, actually. You don't need a screen there. The concept of DirectX is completely loose of screen. You do not tell DirectX, hey, I want to start at that monitor, and then you render to that monitor. No, these concepts are completely decoupled. Actually, the thing that's handling the displaying of the screen is not actually even called DirectX 12. It's called DXGI. It has some DirectX 12 code in there, very probably, but yeah. Now, the general idea of the output merger, as I told you, it is writing the color values to the render target. Now, it's not only writing them to the render target plainly, it's also doing depth and stencil testing and blending. Now, in general, the idea of depth and stencil testing is to check if the color value needs to be written at all. So, for example, depth testing means that we have one continuous floating point value of a certain width, and we also have one of these same floating point values on a per pixel base, and it is always comparing them to each other. So it's kind of like comparing, is the value bigger, is it smaller, is it equal, is it bigger, equal, smaller, equal, and depending on that result you can actually decide if you want to discard the pixel or if you want to write that pixel. Now, depth testing has way more stuff involved. You can also do depth writing, so if the result is of a certain size, you can actually also apply the depth value that you have on the pixel to the actual depth buffer, so that for the next result a new value, or for the next computation a new value is concerned. And there's quite some stuff involved. Depth testing is that flow chart on the left here. That is kind of like how depth testing works. But the general idea is you have a value that is already stored in your depth buffer, and you have a value that's stored on a per pixel base, and they are compared, and depending on the result, it's written or not. The same is also going on with stencil testing. Stencil testing works in a different way. It is not a floating point value. It is kind of like a logical value. It is most of the time used to mask something. So most of the time you are rendering to the stencil buffer. You're kind of like drawing a shape to the stencil buffer. For example, like a mirror where you want to have some reflection in there. Or maybe from knowing the game Portal, there are portals in here. And what you could do is you could render the shape of the portal to the stencil buffer. And then you're kind of rendering what should be visible from the portal itself, and then you're kind of like using these stencil testing to only display the pixels that are kind of like inside the portal. That's the idea of stencil testing. So this is kind of like a continuous test through the whole screen with a very fine gradual floating point value, while this on the right is kind of like just a masking process. It can do a bit more. It can do substantial operations actually to calculate new stencil values. It's also in combination with depth testing, because depth testing is also used within stencil testing, and it's kind of like used vice versa. You can, I think, as far as I know, could define also the order, what you want to do first, and if you're requiring the first result to be successful. And yeah, it is doing quite some stuff. Now, after both of these depth and stencil tests are successful, it is sent to the blend unit. The blend unit is responsible for taking the current value at your buffer and blending it together with the value that was outputted after the pixel shader and correctly tested with depth testing. Now, by default, you can also disable blending. If you're disabling blending, the output from the pixel shader is straightly written to your buffer without any concerns. However, what you do, of course, want to do is you might want to enable blending. For example, if you are blending translucent geometry, transparent geometry, if you are blending that on top of an existing image, you of course want to have blending on because they need to be computed. Now, blending works in two steps. First of all, each of the individual values is taken and converted with some operation. For example, it can be inverted, it can be multiplied, or anything like that could be kind of like applied to it. So before you kind of like do your blending together, you're kind of like processing each of the values individual, the existing value from the render target and the output from the pixel shader. They're kind of like pre-processed individually, and then they are blended together with some blending operation. For example, additive blending, multiplying, there could be anything, subtracting, and they're kind of like then combined together and then written to the render target. And this is the point where we actually finished, and we have kind of like made one journey of a triangle through the whole pipeline. So that's the pipeline. Just to recap: input assembler, it is assembling triangles. Vertex shader, it is modifying the vertices of the triangles. The hull shader configures tessellation for a triangle. The tessellator takes that configuration for that triangle, converts it to multiple triangles, and basically also multiple vertices, more vertices than there were previously. The domain shader is picking up these newly created vertices and assigning the proper values. The geometry shader can take primitives, for example, like points, lines, or triangles, and convert them to other primitives. For example, triangles to points, points to triangles, lines to triangles. For example, you could use a line and convert it to kind of like a quad that is following the line. Then all of these triangles, lines, points that have been emitted from the geometry shader are passed to the rasterizer. The rasterizer is checking coverage and determining which pixels are affected by the geometry. And the pixel shader then takes these pixels, provides them with a color value, passes them to the output merger that does then do some depth testing, stencil testing, and some blending to combine them properly to the target, to the render target. Okay. So now we have done this small part of that whole chart. But no, you don't need to be afraid. I told you everything on the left has something to do with the data. For example, the input assembler gets a vertex buffer view and the index buffer view. Vertex buffer and index buffer view are kind of like meta information that tell the input assembler how this data is laid out. As simple as that. Meta information, how it's laid out, passed to the input assembler. Now all of these programmable stages here, these are fixed function units that they have a configuration. The configuration is not shown here in general. All of these like functional shaders, they are always using something called a root signature. A root signature is kind of like a definition on how to access VRAM, on how to access memory. And what you can put on the root signature is you can put static samplers on the root signatures. This is kind of like a static state on how a sampler works. You can put arguments on the root signature, for example, constant values like the 4 floating points that we use for the polarizer I ran. You can also attach descriptor tables to it. Descriptor tables are kind of like pointers into VRAM, pointers to pointers actually. And what these descriptor tables are doing is they're kind of like defining, hey, this is a shader resource view, an unordered access view, a constant buffer view, or it is a descriptor table that defines how a sampler should operate. Difference between the static sampler are kind of like compiled into the shader, while the normal samplers, they are used to kind of like be runtime changeable and be runtime configurable on the GPU. And all of these information here on the left is kind of like flowing in that kind of like concept of a root signature into these shaders. And the binding to the root signature is, as you might have already guessed, done with these registers. The registers are kind of like referencing register definitions in the root signature, and the actual root signature is defined in a constant. I don't want to go into the details on how this works, but this is basically telling, hey, the register T0 is a pointer to the VRAM, which is a descriptor table for shader resource views that are actually textures, or in this case, the constant float at buffer 0. This is some static data directly stored in the root signature with values, and it's in general, the root signature is just a block of memory that is defining on how to access VRAM or also to store some basic static data on there. Now, to show you this in the example, for example, come on, open this up. What I've defined, this is basically my root signature. It's actually called the root bindings, but this is actually how the root signature works. These are kind of like the 3 active elements on the root signature. For example, you can see that we have this root type constant. So it's actually a constant that is stored on the root signature. In this case, it's a 4-component float, and the data attached to it is that one. It's kind of like a pointer to the data that it shall automatically put on there. Then you can see that we have a CBV. A CBV is a constant buffer view. This is used for the scaling. In this case, I take a look at my constant buffer, get the resource, and get the GPU virtual address. So I'm getting like the pointer where the address is stored. So now I'm actually having like a proper pointer to a constant buffer view. It is not a table of views. It is a concrete pointer into VRAM. This is working on DirectX 12. This is, however, not working for textures. Textures always needs to be stored in the table. This is what I'm binding here. SRV heap is the shader resource heap. This is kind of like a continuous block of views. In this case, it's views of shader resource views, which is used for the texture. And I am getting the GPU descriptor handle for the heap start, which is basically in general more or less also a virtual memory address. It's not really a virtual memory address, but it kind of like is. So it is basically just a set of pointers, and the root signature itself, I might want to quickly open this up as well so that you see how it works, even though this is maybe a bit too complicated for now. Now this, for example, is the root signature that I have used here. For example, you can see that the root constants, these 4 32-bit float values, were kind of like bound to be 0. It is the first one that's in here. Then I have the CBV, which is a constant buffer view bound at B1. Then we have this descriptor table. The descriptor table is kind of like the element 3. And inside of this descriptor table, we have a shader resource view, T0, and the number of descriptor is 1. This basically means inside of this descriptor table, we have 1 shader resource view, and the shader resource view is bound at the location T0, and it has 1 descriptor in here. You could also have 4, then we would have 4 textures, and I think you can also say undefined, and then undefined basically means there are 0, or actually not 0, they're actually like 1 to infinity in there. Then basically it's completely decoupled. You basically tell it, hey, there my texture stored, and here start at T0 and have however many you like. Just some ways here. Down here is, for example, not again the static sampler. The static sampler, I have defined this here with an X because the static sampler actually does not have an address. The static sampler it's just the static data in the root signature. It is not like bound at runtime. This is why you don't see them, because as I told you, the static sampler is compiled into the shader. Now, this is kind of like the idea, and this is what all of these things are kind of like telling us. Now, here on the bottom, it's getting a bit more simpler. We have render target views and def stencil views that basically just define how our render target shall look and how our def stencil view looks. DTV, def target view, whatever. I think it's actually DSV. Is it? I know. I don't care really. But that's kind of like the idea of the DirectX graphics pipeline. Very simple pipeline on the right with many, many steps that serve different purposes to generate geometry that are then rasterized and provided as pixels, and everything on the left here is just like binding material to actually like bind like resources to the stages that we want to use. And of course, everything is again configured, is not even shown here. Now, as I told you, we also have other pipelines available. I want to go over them very quickly, not very in detail. We have a mesh shader pipeline and a compute shader pipeline. Let's start with the compute pipeline. The general idea of a compute pipeline is that you just have one element of a programmable shader. So if you're comparing that one to, for example, that one, you're going to see that we are just having this part and one programmable shader. Now, the idea is that the compute shader, it has no kind of like pipeline step that flows into it and no pipeline step that it flows out of that. So the general idea is that the compute shader is kind of like an unbound workload on the GPU. You have no input data, you have no output data. The idea is that you are just working on your resources here. For example, we have the UAVs, the unordered access views. These are actually kind of like pointers to data that we can read and write. And the general idea, what you're doing is most of the time consuming SRVs and UAVs to produce data into UAVs. I'm going to get to this as soon as we need this, but the general idea, it is just like one step from the whole pipeline. And that's everything that you need. For example, a very interesting thing that's actually happening, I think as far as I know, Unreal Engine with like the latest Nanite is actually like doing their rasterization in a compute shader and accessing the back buffer as a unordered access view. So basically what they are doing when they are rendering their Nanite geometry, they are basically writing to the render target using an UAV. And then later on, this is like consumed for lighting by Lumen. I don't know how Lumen works, but I know that they have re-implemented. They're not using the rasterizer because it was not fitting for them. This is something that you could do in a compute shader. You're basically completely free of the pipeline. However, you can also not use the pipeline, right? I cannot use the tessellator from the compute shader, cannot use the input assembler, cannot use the output merger or the rasterizer. It doesn't work. If I want to work with these components, which I need at some point or should with at some point, I need the graphics pipeline. If I want to do some general purpose work, I can use the compute pipeline here. Now we are coming to the last edition of the pipelines that we have, the so-called mesh shader pipeline. This pipeline is so new, it's actually not that even so new, but it's not even documented in MSDN or Microsoft Learn, how it's currently called. First of all, they called Doc and Learn, and however Microsoft tends to rename the documentation every like 5 to 10 years. Don't know why. Yeah, but the general idea here is you no longer have all of this shit with the geometry. Previously, all the geometry stuff needed to flow to the pipeline. We had the input assembler, which required some vertex and index buffer, which was then kind of like transformed by a vertex shader, which always needed to be there. And then you could optionally have some tessellation pipeline, optionally some geometry shading pipeline, and you were always bound to that workflow. So, the problem was that sometimes people wanted to craft geometry out of thin air. And crafting your geometry out of thin air doesn't work. For example, the pipeline of doing meshlets, and which is also the concept of the new Nanite rendering. This would require you to actually craft geometry without vertex and index buffers, because these meshlets are kind of like dynamically selected and dynamically computed depending on some data and some massive workloads. So in general, this pipeline is for many work. It's not good to have this kind of like pipeline for all of your workloads. At some point, you want to do this all manual. And this is why the mesh shader pipeline is here. The mesh shader pipeline replaces all of the existing geometry data, including the tessellator and input assembler, with an amplification shader and a mesh shader. Now, the general idea is that the amplification shader is a compute shader. So the amplification shader, in general, it is a shader that you invoke with some parameters that you define. The amplification shader is then running its program, and it is kind of like scheduling geometry. So the amplification shader, it takes a look on what geometry do I need? All right, I want to have that many triangles, that many points, lines, whatever do I want to have. And it kind of like tells the part of the pipeline, the so-called mesh shader, hey, I have geometry for you. And the idea of the mesh shader is then to take the geometry and shade the geometry. So the actual meshes that you then get. I think that can be of any, maybe even of any order that is possible. And the mesh shader, what it does is at some point, it is producing geometry that can be consumed by the rasterizer, in this case, like points, lines, or triangles, and it's passing them on to the rasterizer, and then the classical pipeline continues. So in general, it is basically suitable for all workloads that are not fitting the concept of what we have here. So if an input, if the input layout would be a problem, so if vertex buffers and index buffers are kind of like a compromise for you that you need to do just in order to render your stuff, you can say, all right, I don't want to use that concept, I use that pipeline. I mean, like all of the other parts, most of the time it's more like about the input assembler. Really, if we want to talk about that, input assembler is the only reason why we use the mesh shader pipeline. If we do not want to follow the default vertex and index concept at an initial data for the pipeline. Because everything else is configurable, right? We can stripe out all of these here. If we want to have the geometry shader, we can do this. We can do this in the amplification shader. I think maybe even in the vertex shader, but I'm not quite sure of that. If we want to do tessellation, then we, I think, need to stick at a classical pipeline. Not quite sure if we can actually call it tessellation from the amplification shader. We might be even able to, but I'm not sure of that. I actually haven't used the pipeline at all. But the general idea here on that pipeline is it's a more modern way of rendering for certain workloads. We're going to use a legacy D3D12 graphics pipeline for quite a while. Maybe we're going to go to mesh shading at some point, but I'm not quite sure. I think that the legacy pipeline will fit us for quite a long time. But still, it's not really a problem, because we can use it at any point we like. All right, so there we are. End of this video today. It was a massive video. I hope it was helpful, understandable, and usable for you, and it wasn't too much. I tried to get this under 1 hour, but sorry, didn't manage to. Thank you for watching. If you enjoyed, please make sure to like and to subscribe to the channel. It will really help. I know people always hate the begging, but really it helps for me because I want to make more videos, more frequent videos, and dedicate more time to YouTube. And this can only happen if you watch, like, comment, subscribe, etc. You know the game, right? Because more views are more money for me, and more money means I earn more money and I can reduce daytime jobs, so to do YouTube. So thank you for watching. See you in the next video. Have a nice day. Bye.